Good morning to everybody, and so welcome to this seminar entitled Modeling and Control of Autonomous Underwater Vehicles in Industrial Case Study. So this seminar is part of Road to CDC seminar series, where CDC is a conference decision and control and will be introduced later by the speaker. And this is supported by IEEE-CSS Italy chapter, namely the Control Society, Control System Society. So the topic of this seminar is particularly important. You have to know that underwater vehicles are really important today for different applications like exploration, rescue, and others. So for this reason, it's particularly important to develop control of these autonomous underwater vehicles. But you have to know that the underwater environment is particularly challenging because of different circumstances like marine currents and so on, disturbance that we have also in the underwater environment, and like also the possibility to have just a reduced view of the environment. And because of this, of course, you can understand that control is particularly important in order to control these vehicles. One of the techniques, of course, which is important, especially this is comes from the 60s, but in the 60s you have the first results on model predictive control, and indeed in 1978 you have Richalet with the first publication, and 1979 you have Shell company, oil and gas company, who publish other important topics of this technique, control technique. Why it is particularly important apply model predictive control? First of all, you have to understand that because of the uncertain conditions of the underwater environment, modeling of the underwater vehicles are particularly challenging. First, so once that you have the model, you have to design the control, and the control in this case is based on the model. Okay, but despite of the model-free control, model-based control is particularly accurate, and for this reason, it's preferable in a measured situation that you have. So the model predictive control has the advantage to be based on the mathematical model of the vehicles, and so the control problem can be reduced to an optimization problem, and especially we can take into account also saturations of the input, for instance, and of the states in this kind of technique. So the today's talk is will show the effectiveness of the model-based control techniques in the real-world industrial application, and the practical design aspect will be discussed during the presentation. I would like to introduce the speaker, Dr. Luca Cavanini. Luca Cavanini received his PhD degree in Automation, Information and Management Engineering from the Università Politecnica di Marche in Italy, is here in Ancona, in 2018. And he worked as technical consultant and industrial systems and control Ltd of Glasgow, and he is research fellow at this university. His research activities includes model predictive control, okay, autonomous mobile robotics and artificial intelligence, and machine learning techniques for control system. So, dear all, I'm proud, and I'm going to introduce Dr. Luca Cavanini. Luca, the floor is yours.
Thank you.
Mike.
Thank you. So welcome to this first seminar. In this first seminar, we will discuss about the design and development of the control system for an underwater vehicle. In the second seminar next week, we will discuss the development of the path planner. This seminar is within as mentioned by Professor Monterio, is within the seminars organized by the IEEE Control System Society Italian chapter for within the Road to CDC initiative for the CDC conference, the Conference on Decision and Control, that will be held in Milan in December this year. Further, the CDC and the CSS is promoting this initiative about the best master thesis that will be open to the worst set of students that will achieve their degree this year, and they have this deadline of the 1st of November to participate to this competition. So this seminar is on the design of a control system for an AUV. This activity and the result and the design I will present you is related to an activity developed within the Industrial System and Controls, a company of Glasgow, and Mitsubishi Industries. In our activity, the goal of our control problem is to develop a control system for an AUV aimed to perform a certain set of tasks in autonomy in underwater scenarios. In particular, the vehicle that you see here below in this slide is used for evaluating the state of health of oil and gas tubes on the seafloor. Further, this type of vehicles is used for developing and realizing different applications that requires a high degree of autonomy of the robot. Here, in our approach, the control problem is related to the world control problem that will be faced and described and discussed today in the next seminar, is to develop this control system and a related path planner, so a higher control system in the control system hierarchy, that will permit to perform a particular task. The task is indicated here in this slide. The idea is that our AUV is moving from a given position far away, and at a certain time, it needs to be connected to an ROV, a remote operated vehicle, in the underwater environment, of course, that will catch our vehicle for recharging the battery. To move from the initial position to the ROV position, the vehicle will perform a set of tasks, a set of maneuvers related to the capability to detect the position of the ROV with respect to the range of measurement of the sonar. Because of this, the vehicle should be able to correctly track the trajectory generated by the path planner to follow the different waypoints indicated here in the slides, and also while moving through the waypoints, the vehicle will maintain the ROV, that is our goal position, within the range of measurement of the sonar, so on the angular range of the sonar. Further, because we are in the underwater environment, the vehicle is also subject to a current. This current, this tidal current, is defined in specifications and is oriented with respect to the orientation of the ROV, so the final orientation of the vehicle, with respect according to a given angle, and is specified also a given maximum speed for this current, because this current will affect the dynamics of our system with respect to the orientation of the ROV. It means the current will affect the dynamics of the system over different directions, and we need to take care about this to correctly perform this docking task. So, to develop the control system aimed to drive the asset of our vehicle, we need to, first of all, study and develop a simulation model of our robot. To develop the simulation model, we need to define three main aspects. The first is to define the reference frames characterizing our application. Then we need to model the dynamics of our system. To model the dynamics of this system, we will exploit the design framework for underwater vehicles proposed by Professor Torfossen from the NTNU. Finally, we will characterize the vehicle by including the dynamics model of our actuators, because as you have seen, and we will go in depth in this, as you have seen in the previous slides, our vehicle is equipped with several actuators, so it's redundant in some way, and we need to adjust the control action for different actuators to guarantee the correct control performance of the vehicle while moving over the scenario. So first of all, the reference frames. For marine applications, we used to develop and to use two reference frames. The first reference frame is the robot-based reference frame, is the local reference frame that is used for representing angular velocities and lingular velocities of the robot. This reference frame, indicated here in this figure as body fixed reference frame, moves together with the robot and is related to the external reference frame here by a transformation of coordinates. The overall model of the system will merge the combination of the local and the inertial reference frame and the local reference frame for correctly defining the pose and the angular position of the robot with respect to the external one. The signals we are considering on both reference frames are the forward velocity of the robot, the lateral velocity, and the vertical velocity of the robot, with the z-axis in this case oriented in opposite direction with respect to the surface. And the same analysis is performed for defining the external reference frame or inertial reference frame. The different angles we have to control and mentioned here in the reported here in this figure are the well-known pitch, yaw, and roll angles and the different velocities over these angles. Of course, for moving or for mapping our signals, our coordinates from a reference frame to another reference frame, we will exploit the well-known transformations among reference frames that are reported here and here are used for mapping angular velocities and linear velocities from a reference frame to the inertial reference frame. But the real crucial part of this first talk is the design of the model of the vehicle. Our AUV is modeled as a rigid body characterized by this general well-known equation. This equation is characterized by the different effects we want to model to correctly represent the dynamics of our system. So this equation and the dynamics of our system is characterized by the effect of the restoring forces that are dependent on the geometry of our model, of our vehicle, the added mass that is strictly related to the application we are considering, so underwater scenario application, damping terms, coriolis effects, and actuator forces and moments. In particular, we will spend a while in the following slide discussing about the capabilities of actuators to generate the desired thrust that will be mapped in the forces and moments that are represented here as tau A and permit to correctly drive the vehicle. This general rigid body equation is characterized by these components. So M represents the mass matrix component of our equation, and this M is not only related to the mass of the vehicle, but also to the added mass, and we will discuss this later. C represented the coriolis effects. D represented the damping effects affecting the vehicle. G corresponds to the restoring forces and moments, where the restoring forces and moments includes both the gravity force that tends to move to the seafloor, the vehicle, and the buoyancy that tends to move to the surface, the vehicle. As I said, we have the thrust expressed in terms of forces and moment that will be the set of actions we are applying for driving the vehicle. And also, of course, we have the set of state variables affecting each of the terms, where v is the array of linear and angular velocities, and theta is the array of linear angular positions. First of all, the mass. The mass of the vehicle is in underwater vehicles is characterized by two terms, following the approach for modeling proposed by Professor Possen. And in this approach, we can consider the mass of the vehicle as a constant part due to the inertia of the system, so the mass of the system and its size, with respect to the center of gravity, where R is the position of Rg, is the position of the center of gravity of the vehicle. This constant term, and this is interesting for us from a control system point of view, the mass, there is the first term we are considering, we are analyzing in the rigid body equation. It is composed by two terms. This first term is constant, and is parameterized according to this representation, but it's composed also by another term indicated as MAM. This second term represents the added mass. So it is the mass related to the displacement of the vehicle in the underwater scenario and to the water moved while the vehicle is moving. To model the added mass, we can consider a set of coefficients that are typical in underwater application and permit to approximate the added mass by this set of constant coefficients that are provided directly from, in this case, from MHI for characterizing the system. So the first term characterizing the rigid body equation of our system is given by a set of constant elements. The second term we are studying is the Coriolis effect. Now, the Coriolis effect, as indicated in the previous slide, is function of the velocities of our robot. So in this case, from a control system point of view, we are considering this C of V as a time varying component affecting the dynamics of the system. Also in this case, the Coriolis effect can be mapped in our model by considering two components. There are the Coriolis effect due to the nominal mass and the Coriolis effect related to the added mass, as for the mass effect we have seen before. So we can model the Coriolis effect by considering these two components. They are characterized by this skew symmetrical parameterization, and this will permit directly to evaluate what is the degree of change of our C matrix with respect to the range of variation of our angular and linear speed. An analysis like this that permits to evaluate the change of magnitude of the values of the Coriolis effect matrix is useful because evaluating the rate of change and the magnitude of this term, we can evaluate the required robustness of our control system, because we'll see this in the following, our control system will be formulated by considering a certain parameterization of the overall rigid body equation related to the capability of this model to reflect the real world behavior of the vehicle, directly related to the dynamics of the system. So by having an a priori knowledge about the dynamics of the system, so the range of variation of velocities or linear angular velocities, we are able to evaluate how much these terms will change in our reference model for control design. And then we are able to evaluate if a particular modeling approach and control approach is feasible for this case study. Further, we have the damping effects. Damping effects. They are related to different effects affecting our vehicle in the underwater scenario. So in general, in marine vehicles, the damping effects are related to, classified really as potential damping, viscous damping, wave drift damping, vortex channeling, and lifting forces. Now, certain of these components will be removed only because our vehicle is an underwater vehicle, and in example, wave drift damping will be neglected by our analysis because it will affect only surface vehicles. So by the analysis and the review of these different effects and based on the study of our control scenario, the damping effect will be modeled as indicated in this equation. So by a set of constant terms that characterize the vehicle and are studied by the finite element analysis of the hull of the vehicle, and non-linearly related to angular and linear velocities. In particular, we can see that almost every term is related to the absolute value of the linear velocity times the value of the linear velocity. So these equations are nonlinear equations that we need to take care and take into account while modeling the system. Further, as I mentioned before, we have the restoring forces. Restoring forces are related to the mass of the vehicle that tends to move the vehicle to the seafloor, and to the buoyancy that tends to move the vehicle to the surface. Both these forces should be mapped within the vehicle model according to the position of the center of buoyancy and center of gravity of the vehicle. What does it mean? This means that the center of gravity of the vehicle is related to the geometry and to the mass of the vehicle, and in general, it can be different from the center of buoyancy because the center of buoyancy also is related to the geometry, to the mass and to the distribution of the mass of the vehicle, but in general, they cannot be coincident. In fact, if we take a look to the equations characterizing our restoring forces models, we have always the difference in the different terms between the gravity force and the buoyancy affecting the vehicle over the different directions, so related to the forces and moment applied by the combination of these forces. In particular, if you look at the moments, KR, MR, and NR, you can see that the moment generated by the gravity force and the moment generated by the buoyancy are related to YG and YB, and so on for MR and NR. So zeta G and zeta B, XG and XB, where these three terms and these three terms represents the distance between the center of mass of the vehicle and the center of gravity and the center of buoyancy. So based on this equation, we can compute the moment affecting the vehicle over the particular direction. Of course, it is also related to the instantaneous angular position of the robot with respect to the reference frame, because of course the orientation of the robot over the three axes with respect to the three axes affects the forces and moments affecting and characterizing the behavior of our robot. So these are the four terms we are describing and modeling for emulating and studying the dynamics of our model. Now, our model should be characterized also considering the forces and moments that we are defining for controlling our robot. These forces and moments are generated by thrusters. In our case, as you can see from this figure, the robot is equipped with a main thruster on the extreme of the vehicle, fins, two sets of fins. There are rudder and stern planes that are close to the main thrusters, and side thruster indicated in the figure as front thruster and rear thruster. This front thruster and rear thruster are posed in at the extreme sides of the robot and are able to generate forces for to guarantee the hovering of the robot while moving with low speed. So they are used mainly while the robot is approaching to the docking station, to the charging station. Let's go to characterize the actuators to evaluate their dynamics and to understand which kind of control system we need to develop, also for taking into account nonlinearities and the size and the position of these actuators with respect to the vessel hull. First of all, the main thruster. As I said, the main thruster is posed to an extreme of the vehicle, and the main thruster is able to generate only forces for moving the vehicle with respect to the forward direction. Now, our main thruster is characterized by this nonlinear equation characterizing its dynamic. So we have a dynamic part related to a second order dynamics. Sorry. And because the thruster is for underwater application, it is also the force generated by this thruster is also characterized by the water density that is assumed constant in our application, and with respect to the control input. Now, the control input of our thruster is limited to be within an upper bound and a lower bound, but also it is characterized by a dead zone in the around of 0 with an offset of 400 RPM. And this is something we need to take care while developing the control system, because the saturations and dead zone are effect on nonlinear dynamics. We need to take care for having a correct behavior. But further, there is another interesting aspect that is related to the capability of the actuator to generate the expected force. In fact, if we consider the term KT of the J, we can see that with respect to the value of J, so essentially with respect to the instantaneous velocity of the thruster, the force generated by the thruster will be characterized by a different relationship. So we could have a dynamic switching between this equation of KT equal to minus 0.46 J plus 0.66 and the other one where KT is only minus 0.46. Further, we should evaluate if this actuator can be correctly driven to guarantee the required force to be generated for moving over the forward velocity the vehicle. And this will be studied and exploited during the definition of the control policy. Then we have fins. Now, fins are placed close to the main thruster, and the capability of each fin to generate a certain force and a certain moment with respect to the rigid body dynamics orientation is given by these equations. As you can see, here you will not have the term related to the force generated with respect to the forward direction of the vehicle. And this is because due to their position on the hull, fins cannot generate a force over the forward direction of the robot. But they can be used in combination for generating different forces and moments over the other directions. In particular, in this robot, we are able to control each fin, so each rudder and each stern plane in combination, but also individually. So here we have the different delta R1, delta R2 that are related to the angle of the rudders, and delta S1, delta S2 they are related to the angle of stern planes. An interesting aspect is related to the other effects characterizing forces and moments generated by fins, because when we drive these fins for generating a certain force over certain moments with respect to a certain axis, we will have also a part of the force generated that is not strictly related to the control signal driving the fins, so delta R and delta S, but related to the interaction between the fins and the environment. And this part of the forces moment generated due to the use of fins should be taken into account to correctly define the control action driving the fins for obtaining the expected forces and moments. And we will see this during the control system design in a few slides. As I said, in the previous slide, we have seen forces and moment generated by fins, but fins are also characterized by a low pulse dynamics. So each fin is driven as a second order system characterized by a natural frequency of 4 Hz and damping factor of 0.7. This means when we drive our, as we have done, or we will do really, for the main thruster, when we define the control system for the rigid body, so for the vehicle, we need to take care also of the dynamics of fins, because the effect of the change of angular position of each fin is not directly mapped in forces generated by fins, but they are smoothed due to the presence of these second order dynamics characterizing the movement of the fins. And of course, fins are also characterized by a maximum and minimum orientation. So the control action driving fins should be constrained to be between 30 and minus 30 degrees with respect to the zero position of each fin. As I said, we have also another set of actuators. There are the side thrusters. The side thrusters, characterized by specification provided by MHI and also to be used according to this specification, should be this thruster should be used only while the vehicle is moving with a low speed, such that fins are not effective. So by using side thruster, we are able to maintain a given position, an hovering position on the underwater environment, or moving over the environment with a limited forward speed, but guaranteeing the possibility to correctly maneuver the vehicle also when fins are not effective, because the speed is too low. The effect of different side thruster should be mapped in the effective set of forces and moments generated by these thrusters. So here we have the so-termed allocation matrix that permit to consider which is the effect of forces applied or generated really by each of the side thruster with respect to its position on the vessel. Because of this, we can see the first row of this matrix is 0 because side thruster cannot be used for generating a speed for moving in a forward direction the robot. The second and the third row represent the capability or how we can map each force generated by each side thruster in related forces used for moving on the lateral side or over the vertical direction our robot. Whereas the last 3 rows indicates the capability to combine the forces generated by each side thruster to generate moments. Of course, they are related to the position of each thruster with respect to the center of mass of the vehicle. Because of this, we have this combination of df and minus df, and capital DF and capital and minus capital DF and capital DR and minus capital DR. They are related to the angle, to the displacement between the center of mass of the robot and the position of the thruster, and to the again are related to the position of this thruster with respect to the x-axis of the body fixed reference frame. But this equation permits to characterize the combination of forces generated by thrusters, but the thrusters again are dynamic systems and they are characterized by a certain dynamics. In fact, these systems, each thruster is characterized by a dynamics behavior given by the space state model. This is in continuous time. And further, this space state model is used as a filter for filtering the real thrust generated by each side thruster, where the real thrust, indicated with YT here, is computed with respect to the instantaneous value of the control signal driving the actuator, UT, and also the square of the control action. So again, also in this, for this thruster, we have a nonlinear relationship we need to take care while developing the control system. In particular, we also have another nonlinearity related to the operating point of our robot. In particular, if our control action is larger than 1.5381, then the terms coefficients characterizing this mapping between the PWM signal and the thrust generated by the thruster will switch from a value to another value. So we have a switching behavior of the thrust generated by this actuator related to the instantaneous operating condition. And also, this is an aspect we need to take care for generating the correct thrust while the vehicle is moving with different velocities. Finally, we have sensors in our system. The vehicle is equipped with sensors permitting to detect, to measure really, the orientation, the position, and the angular speed and linear speed. And here we have the specifications. In particular, we have a delay of 20 milliseconds affecting the sensors. So we can measure the position and the angular orientation and velocities of our robot with a delay of 20 milliseconds. In our application, in the final control system, the sampling time of the control system will be larger than this 20 milliseconds. So this delay does not affect the control performance because it's neglectable in some way. And further, we have a certain accuracy of sensors permitting to measure both linear velocities, but also angular velocities and angular positions that are considered and included during the analysis of specifications and evaluated for defining the realistic expected control performances. But because of the small magnitude of this angular position and velocity accuracy, this is something we can in some way neglect, whereas the 0.1 meters per second is something we need to take care, because our goal is to maintain the velocity of the vehicle while moving within a certain bound of the reference system, and this certain bound will be always between 0.1 and minus 0.1 with respect to the reference value. But so if we can drive the vehicle within this bound with respect to the reference velocity, we have satisfactory performances. As I said at the beginning, our robot moves in the underwater environment with a depth measured than 3 meters. That means we can neglect the wave effects, but we need to take care tidal currents. In provide the specifications, our tidal current is constant over all the control scenario, and it is oriented with respect to the final goal, so the final orientation of the robot when it reaches the charging point. For including the tidal current effect within our rigid body, we can compute the difference between the actual velocity of the robot and the tidal current velocity and replace with this difference directly within the rigid body equation. And this will permit to correctly map the effect of this disturbance on the dynamics of our robot. As I said, the tidal current is characterized by a set of detailed specifications indicated here as 3 remarks. So the tidal current is constant in direction and velocity, so, and is also rotational. So this is constant with a given orientation with respect to the external reference frame. And also the tidal current affects the robot only with respect to the y and x position. So we can neglect the effect of the tidal current over the z-axis. The maximum speed of the current is considered 540 meters per second, but this maximum speed is given by the combination of the 2 components of the tidal current over y and x orientations. So Pt is the maximum we have, but u of t and v of t can dynamically change because u of t and v of t are related to the angular position and orientation of the robot with respect to the direction of the current. Which is the direction of the current? According to the provided specification, the current has the same orientation of the docking station of the ROV, and also there is an offset that will vary, but is constant over the simulation, between minus and plus 0.7045 radians. That means the current will counteract with respect to the movement of the robot while approaching the docking station with a certain offset in terms of angular position, of angular orientation of the current. So, given that, we can evaluate how to develop a control system for such a type of application. for driving this model and taking into account the different nonlinearities and actuators specification and linearities and dynamics to define the controller. As I mentioned before, this controller will be the controller we are describing is the asset controller. So it's the controller aimed to maintain the vehicle to a given angular position with a certain speed. So the idea at this point is to structure our control system in a way that permits to correctly take into account the different nonlinearities and the time varying dynamics of our AUV. Here we have our AUV affected by this tidal current that is constant over the particular scenario, but in general it is not constant a priori, so it's time varying with respect to every run of the control system. Here we have the structure of our control system. It is characterized by the presence of three main elements. There are the controller, the thrust allocation, and the Kalman filter. The controller, the MPC, permits to compute the set of virtual forces we want to apply to the rigid body for correctly tracking the reference set point. The thrust allocations permit to map these virtual forces into the control signals driving actuators, taking into account the different nonlinearities characterizing the actuator. And further, the Kalman filter permits to estimate the estimated state of the system to be used within MPC. Now, why we are using this structure? In general, MPC and thrust allocation are two control systems based on optimization. So when we use MPC, we will to combine the control problem of mapping the virtual forces moments into real control action driving actuators. We can map the thrust allocation within MPC. But there are several issues on this. The first is MPC, in this case, takes as a set of control signals, so forces moment, 6 variables. If we map the thrust allocation within MPC, we are taking into account 13 variables. So the number of optimization variables in MPC increases, and this will reduce the will increase the computational complexity of the overall control system. The second problem is related to the role of the thrust allocation, because thrusters, as we have seen, thrusters, I mean actuators, equipped with the robot, are featured by several nonlinearities that we need to approximate, at least locally, for correctly representing the relationship between expected force or moment to be generated and control signals driving actuators. And with control signals driving actuators, I mean the angles of fins, the PWM driving side thrusters, and the control signal driving the main thruster. So different types of signals. Because for mapping the dynamics of these actuators in the control law, we need to take care of different operating conditions of each actuator, taking into account the previous control action or the particular operating condition of each actuator. We prefer to split the control problem, the optimization problem, in an MPC and in a thrust allocation. And this permits to increase the effectivity of our mapping between virtual forces and applied control actions. Further, there is another advantage of using MPC and thrust allocation as two different control policies and neglecting a single optimization problem. And it's related to the complexity of the optimization problem, because, okay, the thrust allocation takes as output, consider as output the set of signals driving actuators and MPC virtual forces. In general, in optimization, when we have a large optimization problem and we try to split it in several optimization problems, these smaller optimization problems are characterized by a total computational complexity that is lower with respect to the original MPC. So by splitting the problem into different optimization problems, we are reducing the overall computational burden required for computing the overall control system. Of course, by splitting in this way the optimization problem, we are also accepting a certain suboptimality of the solution. But this is acceptable because the approach we are using for defining the MPC and the trust allocation is suboptimal, but effective enough and simple enough to run on the prescribed control board. In particular, we start with the MPC, with the Model Predictive Controller. For developing the MPC, for this particular application, we consider to apply the linear parameter varying modeling approach. Why? Because by casting a nonlinear model in an LPV model, we are able to formulate our predictive controller in a quasi-linear form. I mean, the linear parameter varying model predictive control will be comparable in terms of computational complexity to the linear MPC, when the MPC is characterized by a linear time invariant system. This has the advantage to simplify the control problem and to simplify the computational complexity of the overall control system, but of course we have the issue of increasing a bit this computational complexity with respect to the linear MPC case, because we need at each time step to rebuild the whole set of matrices characterizing the model to be controlled, and then to rebuild the QP problem characterizing our MPC. But we tested it, and the approximation is effective enough, also considering the sampling time and the dynamics of our system. So what we have done is to, from the original rigid body equation to a space state form that is suitable for developing the LPV MPC. This space state form will consider a set of state arrays that are indicated here, and we have as space state vector the set of linear and angular position of the robot in the inertial reference frame, and the linear and angular velocities of the robot with respect to the local reference frame. The set of measured output is related to the measured positions and velocities, measured because they are provided by sensors, so they are affected by noise, and the set of virtual forces driving the rigid body dynamics. This means that for developing the MPC, we are neglecting the presence of actuators, and we are considering to control directly the rigid body by applying a set of forces. And the output computed by the MPC will be represented by these forces and moments. So, starting from the red equation, there is the rigid body equation. We casted it in a space state form, in a time varying space state form, where A, B, C are the well-known space state matrices, and D is the disturbance matrix related to the effect of the buoyancy and the gravity on the vehicle. So we moved from a continuous time domain to a discrete time domain by the well-known discretization by the Euler method. But for defining the LPV model, formally, we need to define a set of scheduling parameters. These scheduling parameters for us are directly the set of variables defining the state of the model. So our LPV model is really a state-dependent model where the nonlinearities are related to the dynamics of the state. So the scheduling parameters are related to the future, to the actual, the future behavior of our vehicle. Because of this, our LPV model that will vary at each time step is parameterized and is customized and is used for developing and rebuilding the MPC at each iteration based on the estimated state variables provided by the Kalman filter. So, given the previous LPV model, we can develop our MPC. Our MPC is formulated as an optimization problem with respect to the control action. Here we have the baseline formulation of the MPC we applied to this control problem. So we are weighting the rate of change of the control action, so the rate of change of forces and moments, and also we are weighting the tracking error between the controlled signals, controlled output variables, and the reference variables. This is formulated with respect to our instantaneous value of the LPV model, and also we are including a set of constraints for limiting the performance of the vehicle and to guarantee the performance of the control action defined by the controller. So we defined a set of a convex set of constraints for the rate of change of the forces, of virtual forces and moments computed by the MPC, a convex set of constraints related to the magnitude of these forces and moments, and also a convex set of constraints representing the bounds related to the controlled variables. Note that here I refer to the problem with constraints as a convex problem because by exploiting the LPV modeling approach, our model is linearized at each iteration, and then also constraints and the cost function are convex. So the overall control problem is convex and can be solved effectively by well-known methods as the active set method or other solvers. Here we have the explanation of the well-known calibration terms of an MPC. So the set point, the predicted output, the weight matrices, weighting the control action, rate of change, and the tracking error with respect to the reference signals, and the prediction, the control horizons, and the different sets. Note that in our application, and we will see this also in the following when we have the numerical values of this tuning parameter, we considered to maintain constant the LPV model over all the prediction horizon. And this is because in our application, the LPV MPC, as I said, considers as scheduling parameters the variables characterizing the state of the model. So we are not directly able to predict the future dynamics of the system and use this scheduling, the predicted scheduling parameters to update in prediction, the prediction model within the MPC. So we prefer to use a constant FTI model, locally linearized with respect to the nonlinear model, and then use it overall the prediction horizon, also if the prediction loses its effectiveness due to this local linearization approach. And this is essentially what I said before. On one side, we split the control problem between MPC and the trust allocation for reducing the complexity of the MPC and for having a formulation of the trust allocation that is more effective and less computationally expensive with respect to the inclusion of the actuators model within the MPC. This introduces a suboptimality. A suboptimality with respect to the ideal case. And in the ideal case, we are in nonlinear MPC, but we did not apply nonlinear MPC because it is too computationally expensive with respect to our quasi-linear MPC. But the advantage is also related to the possibility, as I said, to use to obtain really a convex optimization problem, and this means by reducing the complexity of the MPC by a linearization, we introduce a suboptimality, but this optimality can be accepted in terms of final performances because the final controller we achieved is simple enough to be executed online on the particular application. So there is, as usual in MPC, we have always this trade-off between computational complexity and effectiveness of the model. By using this LPV approach, we are in this gray area, but the performances confirmed we can apply this type of control design to this complex problem for to achieve the expected performances. Further, there is another aspect. The trust allocation is able to map the control action from the MPC to the control action for actuators. The problem is when we use trust allocation, or in general, we are approximating this mapping like this, that is nonlinear, with a quasi-linear mapping, we are including some error in the mapping. So the idea is to evaluate the mismatch in terms between the real case and the linearized case by evaluating the expected behavior of the system one step ahead and comparing it with the estimated state. So we included a modification in the MPC for taking into account the expected prediction error due to the wrong mapping that will be performed by the trust allocation. And this is computed as EP, where that is given by the estimated actual state and by the actual and the state achieved from the previous step estimated state and the evolution of the system driven by the nominal virtual forces, the Vk-1. The difference between these terms provide the expected estimation prediction error. And this prediction error was included within the MPC model, or really within the MPC law, in this case, by adjusting the value of the disturbance factor representing the nonlinear effects affecting the vehicle in the underwater scenario. Because of this, we updated at each iteration this D bar vector with respect to this D of D K vector that is given from the rigid body dynamics with this has been updated by including the this prediction error due to the mismatch between the applied control effort and the expected control effort, where the expected control effort is the output of the MPC and the applied control effort is really what we achieved for obtaining the actual state of the vehicle XAT. Okay. So, in brief, we can recall the whole set of the interesting set of advantages given by the LPV MPC with respect to other methods. Of course, advantages are due to the type of the optimization problem that is convex. And this is an advantage in terms of computational complexity and so on. Because it's convex, and because of the considered approach, we can formulate it in a condensed form that is suitable for embedded computation. In general, the LPV MPC, or every adaptive time-varying MPC, can be approximated or reduced in computational complexity by using explicit MPC. So by defining a table considering obtained by solving a multi-parametric programming problem. And this is a potential alternative to the real-time design of MPC we performed in this project. This at that time, we consider explicit MPC as a possible solution because we had to test the algorithm on the real board for checking the capability of our control board to correctly run the algorithm. Otherwise, the explicit MPC would have been a feasible solution. Other advantages are related to the memory and to the computational complexity of the LPV MPC that is comparable with LTI MPC. So we are in a feasible framework. And of course, the mismatch, as I said before, is between LTI-MPC and LPV-MPC is related to the needing of rebuilding the quadratic programming problem. But apart this initial phase of definition of LPV problem matrices, the optimization problem defined by LPV-MPC can be computed and solved with an effort that is equivalent to the LTI-MPC featured by the a model of the same size. Disadvantages given by MPC in the LPV form are listed here. So we cannot always map with box constraints, so maximum and minimum bounds on variables. We cannot map in this form the real constraints characterizing our system. In example, again, actuators. Our actuator has some dead zone, and dead zones are non-convex functions that in some way we would to include within the MPC while maintaining the convexity. Further, another problem is given by the LPV approach, because, as I said, in our application, the LPV model is considered as constant over a prediction horizon. In principle, we could update it with the predicted shadowing variables. This is a limit, because in this case, the shadowing variables cannot be predicted effectively due to the nature of these variables. So this introduces a certain suboptimality in the LPV MPC with respect to the nonlinear case. Of course, and this is what I said in the slide before at point 5, the computational time is comparable for solving the LTI MPC and the LPV MPC, but we need to take care about the time required for rebuilding the space-state model and related QP matrices. And this will be expensive in certain applications depending on the tuning parameter and on the size of the model. Another issue related to the shadowing parameters, because we are considering we don't want in this case, we don't want to predict the future value of shadowing parameters, but these shadowing parameters must be measured or estimated. So we need an effective estimate of these parameters. But in this case, we overcome this problem because the parameters are the state of the system. The Kalman filter provides effective estimation of this. Further, of course, the real performances of LPV MPC should be evaluated with respect to the nonlinear MPC, because in nonlinear MPC, we are considering the nonlinear model, and the real nonlinear constraints characterizing the system, in LPV MPC we are approximating everything to a convex form. But this is not an issue because we evaluate the computational complexity and the other factors affecting the different MPC solutions, and the nonlinear MPC has been considered a non-feasible solution, solution for this problem. Then this has been the MPC, so a controller trained and calibrated with respect to the rigid body dynamics of the system. Then we need, in some way, map the set of virtual forces and moments to the real set of control signals driving actuators. And because of this, we included the thrust allocation. The thrust allocation is formulated again as a constraint optimization problem. Also, in this case, it has been formulated as a quadratic programming problem, where we want to constrain the set of signals driving actuators with respect to their bounds, so UA minimum and UA maximum, and we want to satisfy this condition because of tau of v is equal to g of t u of a. So we want to take into account that the combination, the instantaneously linear combination of actuators control signals should provide a combined effort in terms of forces and moments that maps exactly the virtual forces and moments generated by the MPC. The problem is formulated as a QP because the Hessian contains, the Hessian here is the matrix W, contains weights permitting to limit the magnitude of the control action driving actuators, whereas the linear term, UC transpose H, permits to weight the mismatch between the expected thrust generated, so the expected force and moment generated by combined actuators, and the signal generated by the MPC. So the linear term represents the capability to track and to satisfy the force and moment demand required by the MPC with the available actuators. So, and this is the explanation of our thrust allocation algorithm. So our optimization variable, our optimization vector really, is the set of signals driving each actuator from the main thruster, rudders, and side thrusters, and rudders and stern planes, so fins, and rear and front side thruster control signals. For each of these control signals to be used for driving actuators, we will have maximum and minimum values in terms of magnitude. Really, these values will be characterized by taking into account also the, some nonlinear dynamics of actuator as rate limiters. So these values are not directly used as the maximum or minimum magnitude, but they are also characterized for representing the maximum and minimum rate of change. Also, there is another aspect, interesting aspect, that is related to the reference forces and moments that are the output of the MPC to be tracked by the thrust allocation, because XV, YV, zeta V, KV, MV, and MV in the last equation represent the output of the MPC, whereas XA, YA, zeta A, and so on represent the additive effects due to actuators. What does it mean? As you remember, These are the equations given by the model of forces and moments generated by fins. Only part of this equation are already part of these forces and moments are related to the control action on the actuators, whereas this terms here represents the effect, the side effects of thrusters in contact with the water. That means tau v, the virtual forces to be tracked, are composed by the yellow terms related to the forces generated by the MPC, and the red term, this red term, are disturbances. We need to take care to be sure that the control action driving an actuator will provide the correct part of forces moment to be combined in the thrust allocation. So because of this, we are scaling of a certain offset due to these side effects of thrusters for achieving the correct control performances. The rest of the thrust allocation matrix problem is characterized by the configuration matrix of the allocation matrix. There is a time varying matrix because the vehicle is moving over time and actuators are moving in terms of angular orientation with the vehicle. So this allocation matrix is used for mapping, instantaneously mapping our control action driving actuator into the related forces and moments. A part of this matrix, that is the last row, this last column, sorry, is related to the allocation matrix representing the combined behavior of side thrusters, whereas G11, left top here, contains the effect, present the contribution of the main thruster, and other signals, GY, other entries of the G matrix, so GY, GZ, GK, GM, GN, and so on, are used for representing the effect of fins. Only the effect of fins related to the control action, because the rest, the side part of the interaction between fins and the underwater environment, are yet included in the previous, as in the previous slide, within the tau v array. And this is time varying also because this permits to take into account the switching between operating conditions. In example here, G11 is continuously updated time by time according to the instantaneous operating condition for correctly mapping how the control action driving the main thruster will reflect in the generated force, and it is time varying according to the switching dynamics related to the instantaneous value of the control action and to the previous value of the main thrust and rotational speed. And this is also something I mentioned before. For each of the limit values describing constraints on the control action driving actuators, we can replace these bound values with the rate, with the updated value of the rate of change, because certain actuators can move with a certain speed, so we can achieve a certain magnitude of the force to be generated because on the internal dynamics of the actuator. So we need to constrain also the rate of change of the control signal driving these actuators for correctly mapping the effect of this local actuator dynamics into our control law. the last part of our control system is the Kalman filter. Now, as you know, the Kalman filter is well known because it permits to obtain certain performances in quasi-linear cases. In our approach, we considered an LPV Kalman filter. There is an extension of the extended Kalman filter to the linear parameter varying modeling case. And this permitted to correctly define and estimate really the different variables describing the position, linear and angular position of the vehicle, and also the different velocities, linear and angular velocities with respect to the local reference frame. So let's see some results. For testing the algorithm, we consider this set of tuning parameters, in particular for the MPC. It's interesting to know that in our approach, we considered an LPV MPC. So the space state model is constant over the overall the prediction and control horizon. For our approach, we considered a control horizon of 1. So only the first time instance is considered for defining the control signal, whereas the prediction horizon has been considered of 10. Here is not reported, but in our application, we included a set of bounds on maximum forces and moments, virtual forces and moments to be computed by the MPC, but these bounds are safety bounds because they are opposed to the nominal maximum thrust each actuator can provide. So to the maximum and minimum nominal forces and moment each actuator, the set of actuators can provide. So are safety bound to stay within the feasible area of operations of actuators. For testing actuators, for testing the control system, evaluating the correctness of the developed control system for the rigid body dynamics and actuators, we considered 2 tests initially. There are a test without the tidal current, so in nominal operating condition where the vehicle is not affected by any disturbance, and a max current test in which the vehicle is moving in the underwater scenario characterized by a current speed that is the maximum with respect to our specification, so 0.5 meters per second, and also the angular orientation of the current with respect to the docking position is the maximum value, so minus 0.7045 radians. And so we can see the performances of this. As you can see on the left, we can see the performance of our system in case of no current. And from this, we can see that the system is able to track our reference signals. In this case, we have a set of steps and a set of constant values for the position of the vehicle and for the orientation of the vehicle. But we can observe that both the angle theta and the vertical position of the robot are not correctly tracked by the control system. And this is due to the mismatch between the model of actuators used within the control system and the real behavior of actuators, because this trade-off between theta and the reference signal, and here the trade-off between zeta and the reference signal is due to the dead zone affecting side thrusters, because in this scenario the vehicle is moving with a slow speed, so the fins are not so effective to generate forces and moments. Because of this, we need to use side thrusters to stabilize in hovering the vehicle. The problem is related to the dead zone, so MPC cannot, the thruster location cannot correctly map the set of forces as moments to be generated by the MPC within the space of control actions of the actuators. And because of this, when we approach to the dead zone, we have a trade-off among virtual and real forces and moments, and this trade-off reflects in this offset in the zeta position and in the theta angle. But both this trade-off in the no current test are within expected specifications, because the original specifications provided by MHI required that zeta, the tracking error for zeta is minor than 25 centimeters, and the tracking error for theta in steady state is lower than 0.05 radians. The same discussion is reflected in the max current test, when we can achieve with slower transients and with an increased number of oscillations for each controlled angle, but we can achieve similar performances. In particular, we can see that the tracking error in steady state for the theta angle is more or less closer to the no current test performance. The same discussion can be done for the zeta tracking error, and also only the peak during the transient is increased of around 3 centimeters, so an acceptable value. Whereas for the phi angle, here we have a small offset in steady state. That is again due to the effect of the current on the vehicle dynamics. If we take a look to the control actuators control actions, we can see the effect of the dead zone. Here we have on the left the no current test, on the right on the max current test, and we can see there are several oscillations of the reference signal driving the main thruster within the dead zone. These oscillations, that are pretty evident also in the max current test, are within the dead zone. So this oscillation will represent the instances when the thruster is not activated, because the policy has been formulated to maintain the thruster off while the control action is within the dead zone. So essentially the thruster, the main thruster, is used only when the blue lines are out below or above with respect to the values of the dead zone. So this oscillation in the middle does not affect the behavior of our actuator. And this would also increase the lifetime of the actuator, because in this way we would avoid the case in which the actuator starts to jump from to move from a direction to another direction in the dead zone, because this would stress more the motor and so reduce the lifetime of the system. These are the results for the fins, for the control of the fins, rudders on the top and stern planes on the bottom figure. As you can see, in our scenario, we are moving with limited forward velocity, so fins are not really effective. So for the major part of this scenario, fins are maintained to the zero position, and only in case of the max current test, the stern planes are used and moved to the maximum angular position. But their effect, the effect of these actuators is limited in this scenario, because the speed is small, so it is expected that it maintains a value close to zero or goes to the maximum, because to the maximum have some, this makes some effect on the dynamics of the system, otherwise it is maintained to zero. And further, we have the performances of front side thrusters. Here we can see how the thrusters tend to stabilize in general to a constant value in both cases, and this constant value is related to the thrust to be generated for maintaining the vehicle in hovering. Maybe I didn't mention this before, but the vehicle is a vehicle with positive buoyancy. It means if the vehicle is left in the water without any actuator, the vehicle will move to the surface. So the goal of side thruster really is not to generate a thrust for moving to the surface the vehicle, but it generates a thrust for maintaining the vehicle to a given depth. And the results for the rear side thruster are more or less the same, because the previous one was the thruster on the front of the vehicle. These are on the backward of the vehicle, so their behavior should be more or less equivalent for maintaining both the depth and the angular orientation, in particular the pitch. The system has been developed and applied to the Mitsubishi Namino D vehicle. This vehicle has been tested at the time, 3 years ago, in a water tank in Japan, and has been equipped with a set of sensors and actuators reflecting the layout of the model indicated by MHI, and the water tank performances of the system that I cannot show because of limits in diffusion of certain informations. The performances achieved on the real system validated the performances of our simulated system. So we have a positive feedback on the design of this low-level controller, or really asset controller, for this type of vehicle. Now, this was the first seminar on this modeling and control of AUV, industrial case study, and this has been based on an activity that involved industrial system controls and Mitsubishi Heavy Industries. In the next seminar, next week, we will discuss the design, the development of the upper level control system of this vehicle, so the path planner. So we will see how we developed a path planner based on model predictive control that permitted to correctly perform the task initially indicated, so moving the vehicle over a set of operating points while maintaining the goal position and orientation, so the goal pose within the range of measurement of our sonar, and also taking into account the effect of the tidal current for adjusting the trajectory of the vehicle and reducing the power consumption due to the use of actuators. And this is what we'll discuss next week in the second seminar we organized. And for today, that's all. Here we have my contacts. So for you and for people from the web, if they have any question, you can write me an email. Otherwise, next week we'll discuss the second part of the seminar related to the path planner and the design of an optimal path planner, including the capability to limit the power consumption, considering the effect of the unknown or unmeasured tidal current on the vehicle.